In this video, we're going to talk about Kirchhoff's voltage law. Now, this is the second law Kirchhoff came up with, and it's going to be a very important tool to put in our tool bag when we're analyzing electric circuits. Now, what is Kirchhoff's voltage law? Kirchhoff's voltage law states the sum of the voltages of each component in a closed loop must equal 0. So let me write that down quickly. Now, I'm going to use KVL as a shorthand notation for Kirchhoff's voltage law. So KVL. Okay, so one more time. Kirchhoff's voltage law is going to be the sum of voltages across each component in a closed loop must equal 0. So we're going to add up all the voltages across every component, and that must give us 0, right? Now, the key word here is going to be closed loop. We must be able to identify the loops. Just like in Kirchhoff's current law, where we had to be able to identify essential nodes, we must be able to identify closed loops. As we work through these problems, I'm going to be showing you exactly what is a closed loop. So don't worry too much if you don't have a firm grasp on that as yet. Let's do our first example, right? It says find VFB and VEC in the circuit. So they want us to find the voltage at the point FB and the voltage at the point VEC. Now, when we look at this, the first thing I want us to identify is we don't have any current labeled, right? We have voltage sources and we have resistors, but these resistors values are also not given, just the voltage across each resistor. Therefore, we know every voltage in this circuit, right? So you might be thinking, why do we want to know the voltages at the point FB if we already know all the voltages? Well, here's the thing. Sometimes you might run into a problem and you just want to find whether the voltage across these particular elements are correct, right? So in this particular instance, they want us to now kind of cut off the circuit. So they give us this circuit, and we know this circuit is one big closed loop, right? So we go back to our definition of KVL. So if we was to sum up all of these voltages, we're going to get 0. You know what? The question didn't ask us to do that, but let's do it quickly, right? We have this one big loop. If we was to perform KVL on our original loop, we should get 0. So we know KVL at, I'm going to call it big loop, right? By the way, this is very arbitrary. You can call it whatever you like. You can call it loop A, you can call it loop 1. It's really up to you. I'm just going to start here, right? I'm going to sum up all of the voltages in this closed loop. Now, I'm going to go in a clockwise direction. So I'm going to go this way, okay? Now, you can go anywhere you decide to go. If you want to go counterclockwise, it's fine. But just make sure that you follow passive sign convention, right? Now, because I'm going clockwise in this direction here, if I am entering a negative terminal, then I'm going to treat it as a negative voltage, okay? So let me start at this voltage source here. Because I know I'm entering this way, right? I'm going to have negative 12. Now, as I continue to walk around this closed loop, I'm going to enter this resistor, which is going to be a positive to negative. So this is a voltage drop. Therefore, I'm going to write it as a plus 1. Then as we continue around this loop, we have another voltage source, but it's going to go from plus to minus. Therefore, we're going to write this as a positive voltage. We're going to have plus 3. Then we're going to have a plus 3 again across that resistor. Then we have another voltage drop from plus to minus. So I'm going to write this as plus 1. Now we have another voltage drop across this resistor. I'm going to write it plus 2. Then we have this final voltage drop across this resistor, plus 2, equals 0. So that is what Kirchhoff's voltage law says. The total sum of voltages across each component in a closed loop must equal 0. Okay? Now let's add all of this up to see whether Kirchhoff's voltage law was satisfied. So we have negative 12 plus 1. When you add all of this up, that's going to give us 0 equals 0. Therefore, Kirchhoff's voltage law is satisfied. Okay, so that's how we kind of take Kirchhoff's voltage law. Now let's go back to our original problem and what the question was asking. It says, find FB and VEC in the circuit. Okay, so what I'm going to do is I'm just going to erase this. I'm also going to erase this. So if you want to write it down, pause the video, and now's a good time to write this down. Okay. Okay, so they want us to find the voltage across these 2 points. Now you might be wondering why. Sometimes we're going to have to isolate a circuit. So that's why they want us to find the voltage across these 2 points. Now you can think of it multiple ways. You can just start to some of the voltages starting from VFB, and you might be able to look at this and say, okay, well, I know I'm going from F to B according to the subscript. So we can say VFB equals, we have 2, because we know we're walking in a clockwise direction, right? And we know we're going to start with 2. 2 plus 2 minus 12. Therefore, you can say VFB equals, when you solve for this, you're going to get -8 volts. That's what some of us may do right away, right? Now, I want us to know this is perfect. You can do it this way, no problem. But what I would like to show you is what we're going to do is we're actually going to draw in a wire, right? We're going to draw in a wire. Remember, this wire is not going to have no resistance. I mean, of course, all wires have some type of resistance, but this type of wire is not going to have any resistance, okay? So we're just going to draw in this wire. Let me use a completely different color. I'm going to use blue. So we're going to draw in this wire here, okay? Now, when we draw in this wire, we know that's going to be for the voltage VFB, okay? So it's going to be VFB. And now this subscript is very important. This is going to tell us that F is going to be where the positive terminal is, and B is going to be where the negative terminal is. So if F comes first, that's where you put the positive terminal. Now, when you look at this, remember what Kirchhoff's voltage law is. KVL is the sum of voltages across each component in a closed loop, and that must be equal to 0. Okay? Now, when we look at this, how many loops do you think we have? Now that we've added in this wire, right? If I was to move this, just for a split second, when you look at this circuit, how many closed loops do you think we have? Well, we have 3 closed loops. Do you agree? Our first closed loop is going to be right here, which is going to be loop 1. Our second closed loop is going to be this loop right here. This is going to be loop 2. So once I added in this wire across these 2 points, it now created 2 loops we didn't have to begin with, okay? So now we have this loop that's going to go on this side, and it's going to have A, B, F, G. And now we have loop 2, which is going to have B, D, F, E. Now we have one more loop, and that loop is going to be the big loop, right? It's going to be the outside loop, which is going to go, of course, all of this. Now, in this particular circuit, right, we want to find the voltage VFB. So it's really up to us how we want to go about this one, right? Why? Because we can either choose this loop, loop 1, or we can choose loop 2. Now, for this particular one, I always like to go with the one that more so has less components, okay? So I'm going to just do KVL at loop 1. When I write this down now, I'm going to have KVL at loop 1. So when I take the KVL at loop 1, I know I'm going to walk around this loop and add up all of the voltages. I'm going to start right at this resistor here, right? I have plus to minus, so I'm going to have a positive 2 volts. I'm going to write this as 2, plus 2, minus 12. Now when I get here, because we're entering the negative terminal for this particular situation, I'm going to write this voltage as minus VFB. VFB equals 0. Now remember, the subscripts are only there to tell you which side is going to be positive and which side is going to be negative, okay? So yes, we're going from B to F. It doesn't matter. That is still the same thing as FB. The only importance of this subscript is to tell you the polarity this voltage should be written at, okay? That's the most important thing. So even though we're going around this loop and we're going to go from B to F equals FB, right? Think about it. You have 3, 2, and you have 2, 3. The same thing. The only difference is this is going to tell us which polarity is going to be where, okay? So we have minus FB. Now remember, we want to solve for FB. Therefore, we're going to say 2 plus 2 is 4. 4 minus 12 is going to give us negative 8 minus VFB equals 0. Therefore, when you solve for this, VFB equals negative 8 volts. So this is the same answer we got when we did it this way, okay? This way was just more methodical, and we went step by step and we used Kirchhoff's voltage law to find the voltage VFB. This is very similar to Kirchhoff's voltage law, but in this particular instant, we didn't really think of it as a loop. We just thought of it as going from point F to point B. In this one, we thought of it as a closed loop, and we walked around the loop and added all of the voltages. So VFB is going to give us negative 8 volts. Now pause the video right now and give this one a try. You know you have two options, right, for this particular situation. You can either walk around loop 1 or loop 2. Okay, pause the video and try to walk around loop 2 to see whether you got the same answer, which is going to be negative 8 volts. Okay, I'm just going to do it real quick, right? I'm just going to erase this. So we have KVL at loop 2. Remember, we still want to find the voltage between these 2 points, FB. So I'm going to take the KVL at loop 2 this time, because I know that this wire, right, this wire is going to make 2 loops, this loop and this loop. And we can walk around any one of these closed loops to find the voltage right here. So let me just do that. So you can start anywhere in this closed loop. I'm just going to start right here, right? So we have a plus 3. As we walk around, we have plus 1. Now, as we continue to walk around, this time we have plus VFB. So we have plus VFB plus 1 plus 3. Plus 1 plus the 3 volt source. And we know that is going to equal 0. Okay? So now when we start to solve for VFB, we know that's going to give us VFB plus, when you add 3 plus 1, that's going to give you 4. 4 plus 1 is 5. 5 plus 3 is 8. Equals 0. Therefore, VFB equals negative 8 volts. So this is the same exact answer we got when we walked around loop 1. Therefore, as you can see, because we had this wire here, it created 2 extra loops. And this actually made our lives a little easier because we had 2 choices to choose from. We can either go this way or this way. I usually prefer to go with the one with least components. Therefore, I probably just would have chosen loop 1. Now, because I know all of the voltages in loop 1, I know I could have just chosen loop 1 because it had the least amount of components. Now, let's say I didn't know this voltage here, and I knew all of the voltages on this side. Then it would have made more sense for me to choose loop 2 because I knew all of the voltages in loop 2. So as you see, there are just different things you have to keep in mind when analyzing these circuits. If you know all of the voltages, then you can choose any loop. If you don't know all of the voltages, then even though one loop might have less components because you don't know all of the voltages, it is going to be better to go with the other loop that you know all of the voltages in. All right, so this is the first part of this question. Now the second part is going to be find VEC. Okay, so this is part B. Now what I'm going to do is I'm actually going to clear off this diagram and start afresh. So if you want to, pause the video, write all of this down, draw this circuit one time, and just for the sake of time, I'm not going to redraw the circuit, but I'm just going to clear it up a little bit, okay? So I'll be back. Okay, I'm back. So for part B, they want us to find the voltage at these 2 points, E and C. Okay, now we know because we're going to start at E and go to C, we can just walk around this like how we did the very first time without using KVL per se. We can say VEC equals, we have plus 1, so we have 1 plus 2 plus 2 minus 12 plus 1. When you solve for this, VEC is going to give us, we have 1 plus 2, that's going to give us 5. 5 plus 1 is 6. Then we'll have negative 12 plus 6 is going to give us negative 6 volts. So that's one way to do that problem. Now, that's not really using KVL, right? Because we didn't take the sum of voltages in a closed loop. From this point to this point is not really a closed loop. Now, if we was to add in a wire, right? Let's say we add in this wire here. Now we have a closed loop. Do you see the difference, right? Without that wire, we didn't sum up the voltages in a closed loop. We just summed up the voltages from point E to point C in a clockwise direction. But with this wire, now we have a closed loop, okay? So now, when we look at this, I want you to ask yourself, how many loops do we have? Well, we know once we put in this wire, we're now going to have 3 total loops. The first loop is going to be this loop right here. I'm just going to label it loop 1. So this is loop 1. Then we also have a loop from C, D to E. This is going to be loop 2. And then we have a big loop, which we can call loop 3. I'm not going to label that one, right? So you have 2 options once again. You can use KVL at loop 1 or KVL at loop 2 between the points E and C. Now, for this particular example, like I say, I always like to choose the loop with the least amount of components, especially if I know all of the voltages within those components. Now, therefore, that would be loop 2. So if I take the KVL at loop 2, we should be able to find our answer. Now, once we drew this wire, it's important that we label the voltage across this wire the way it's supposed to be labeled, right? We know this voltage across this wire is going to be EC. So I'm just going to write it as VEC. Now remember, the polarity is going to be very important. The first letter is going to denote a positive terminal. So at E, or more so closer to this side, we're going to have the positive terminal, right? You know what? That looks like a minus sign. Let me do it like this. So at the E, we're going to have the positive terminal. And at the C, we're going to have a negative terminal, okay? So the order of the words matters, but when we go around our loop, it doesn't matter. So let's do it. So we have, I'm just going to start right here actually at this positive 3 volt. As we walk around loop 2, we have positive 3, a voltage drop. So we're going to have 3 plus, because we're entering the positive terminal, we have the voltage VEC, right? So we're going to write plus VEC. That's the voltage they want us to find. As we continue around this loop in a clockwise direction, as we continue around this closed loop in a clockwise direction, we're going to have a 3-volt source. And because we're entering the positive terminal, it's going to be plus 3 equals 0. Now remember, they want us to find for VEC. So let's simplify this. We have VEC plus 6 equals 0. Therefore, VEC equals negative 6 volts. So this is going to be our answer for the voltage between the points E and C. As you can see, we got the same answer here, which means this way worked as well. Now remember, you can also do KVL at loop 1, right? Because we know loop 1 is going to entail A, B, C, E, F, G. So you can do KVL here. If you want to, you can do it real quickly. You know what? I'm just going to do it with you, right? Let me just erase this. So let's do KVL at loop 1, right? Now, usually I'm not going to keep doing it this way. I'm usually just going to choose the loop with the least amount of components, especially if we have all of the voltages. I'm not going to choose the loop with most of the components, but I guess for an introductory video, it's very helpful. So let's start. Where do you want to start from? I'm just going to start right here. So as we walk around this loop this way, we're going to have a voltage drop. So we're going to have 2. Now, as we continue, we're going to have this 12-volt source. Because we're entering the negative terminal, we're going to have minus 12. Then we're going to go to the 1-volt resistor, which is going to be plus 1. Then once we get here, we're now going to come down this way. So we're going to enter the negative terminal. We're going to write minus. And the voltage across this wire is going to be VEC. So you have VEC. Then we're going to have plus 1 as we continue. We have plus 1 volt across that resistor. Plus 2. And we know we started right here. Therefore, this is where we're going to stop. And all of this should equal 0. So they want us to find VEC. So let's write this as minus VEC. If you do 2 minus 12 plus 1, now let's just add all of the numbers, okay? We have 2 minus 12 plus 1 plus 1 plus 2. That's going to give you minus 6 equals 0. We're going to take the 6 over, so we have minus VEC equals positive 6. Therefore, VEC equals negative 6 volts. And this is the same answer you got when you took KVL at loop 2. So as you can see, there are 2 different ways we can solve this problem. Actually 3. But with the KVL method, there are 2 different ways you can solve this problem. Just be able to identify what is a closed loop. That's the most important thing, right? Once you can identify what is the closed loop, sometimes you're going to have to draw in the wires. Sometimes. If you have to draw in the wires, just draw in the wires. Label the voltage according to the 2 points the wire is going to be drawn at, right? Remember, the first letter is going to represent the positive side, and the second letter is going to represent the negative side. Walk around the closed loop by summing up all of the voltages, and that's how you're going to find the missing voltage. So this is just an introduction to Kirchhoff's voltage law. In the videos to come, we're going to work a slew of problems. I'm not going to take my time as much as I did and explain each thing step by step, because I feel as though the more you work these problems, the better you're going to become at them. So pause the video, write this stuff down. In the next set of videos, we're going to do a lot of examples. So get ready to have some fun. And we're going to put Kirchhoff's voltage law in our tool bag and make sure we have it locked in. See you soon.